Following on from some of the earlier videos, we got to this stage here where when given a strange function like this, we would use the second fundamental theorem of calculus to get to this stage here. So when given a strange function like this, all that you can do in your mind is to visualize the derivative graph. So when given a strange function like this, all that you can do in your mind is visualize this derivative graph. And then from the derivative graph, you have to somehow create your original f of x. And then we got to a stage where when you read this, it is the area from 0 to x. So x could be anywhere. X can slide back and forth here. But as x tends to infinity, so as x tends to infinity, the area of this thing here, will be root pi over 2, and it's not obvious why it's root pi over 2. We will investigate why another time. But the limit of this thing here, the height of this function here, or another way of thinking of it, the limit as x tends to infinity is root pi over 2, and as x tends to negative infinity, it is negative pi over 2. So when you come to read this, the area here as x tends to infinity, this whole area here is the height of this thing here. But this is very useful in statistics. But the thing is, we want to create a new function where we want this area as x tends to infinity. We want this area to be a convenient number 1. So we want to, at the moment, we've got this function here, and it looks like this. It looks like this. The derivative looks like this. But now we want to somehow create a new function where the whole area here, from 0 to as x tends to infinity, we want to somehow create this area to be a convenient 1, because when it's 1, it's very useful in statistics. So we now want to create a function where this whole area here is 1. Well, if at the moment, if currently this area here is this thing here, currently as x tends to infinity, the whole area here is this thing here. So this thing here represents this area as x tends, represents this whole area. Hang on, let me just rephrase this. This whole thing here represents the whole area as x tends to infinity. Well, if the whole area here is this thing here, then we should create this function. You see, if we define a function as this thing times this thing here, then as x tends to infinity, then the whole thing here will be 1. Because, hang on, let me go back one step. Hang on. So at the moment, this whole area here, as x tends to infinity, is given by this. And by the way, this thing here is root pi over 2. Okay, so this whole area here, as x tends to infinity, is root pi over 2. So this whole thing here is root pi over 2. Well, if we want to create a function where this area here is a convenient number 1, then all we have to do is get this thing times 2 over root pi, and then as x tends to infinity, remember x can slide back and forth. As x tends to infinity, this area here will be a convenient 1. So if we define a function, if we define this function here, the area function, if we define this function here as, well, don't forget this thing here, as x tends to infinity, this thing here is oh, sorry, this here should be root pi. Okay, as x tends to infinity, this whole thing here is root pi over 2. But then, because we want to define, we want to create a function where this area here is a convenient one, then let's define the error function, here as being 2 over root pi and then times this thing here. So this function here is very useful in statistics. Okay. There are other functions which we will look at in the next video. Well, we will look at this in the next video. But when you see this, all that you have to work with is that in your mind you have to visualize that this here is your derivative graph, whatever it may look like, and then somehow you have to get to your c of x here. Well, we will investigate this in the next video. Okay.